The common ion effect and precipitation going to be the topic of this lesson. My name is Chad and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep. I'll be sure to leave a link in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the rest of this school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. All right, so the common ion effect and precipitation. This is the second lesson talking about solubility equilibria here. And in the last lesson, we talked about solubility in Ksp and the relationship between Ksp and the molar solubility. But now we're going to find out that when you have a common ion, and we'll define that here. So we're going to do it in the context of AgCl here. So AgCl dissociates to give Ag plus and Cl minus. It's got a fairly low Ksp value, so it's not the most soluble thing in the world. But if I add a strong electrolyte, one that dissociates completely, that contributes either silver ions or chloride ions into the solution, well, according to Le Chatelier's principle, it's going to shift this equilibrium back to the left, meaning I have less solid dissolved, and less solid dissolved means lower solubility. And so the common ion effect means, so having either one of these ions present in the solution from some other source is going to reduce the solubility of AgCl. And that is the nature of the first question here. So the first question says, what is the molar solubility of AgCl? And that's the key part here, in 0.1 molar HCl. And again, the Ksp is given as 1.8 times 10 to the negative 10. Now, I left up the work from the first example we did in the last video so we could see how it's going to be different in this one. And in the last video, before any AgCl dissociates, you don't have any silver, you don't have any chloride in the solution, you increase the amount of both by an amount X so that you end up with an X amount of both. And then you plug those in for the silver and chloride ion concentration, so you get X squared equals 1.8 times 10 to the negative 10, and you take the square root, and you get a molar solubility of 1.3 times 10 to the minus 5. Well, now the big thing that's going to change is that because we've got HCl in the solution, well, you have to remember that HCl is a strong acid, one of the examples of a strong electrolyte. And so when HCl dissociates completely, you get H plus ions, and I don't really care about that, but you get chloride ions. It has something in common with our salt of interest. In this case, because it dissociates completely, well then 1-to-1 ratio here, 0.1 molar HCl is going to have a 0.1 molar chloride concentration. And so before any AgCl even dissociates, we are already going to have 0.1 molar chloride in our solution. Now we'll still get an additional amount X, but then at equilibrium then, 0.1 plus X is simply 0.1 plus X. And so we can't just simply plug X in for the chloride ion concentration anymore like we did the last time. And so in this case, we're going to have 1.8 times 10 to the negative 10 equals the silver ion concentration times the chloride. And the silver really is still just X. But the chloride concentration here is going to be 0.1 plus X. And if I asked you, what is the most mathematically accurate way of solving this? Well, problem is, so you're going to end up with an X squared term, and this is going to be a quadratic, and you got to solve a quadratic, except we are definitely not solving a quadratic. And just like we saw with Kas and Kbs, as long as your K, your equilibrium constant, is really small, well, then that reaction is going to favor the reactants, which means the amount X, so that shows how much of the reactant actually turns into products, that should be small as well. And so again, because we have a small K value, we can infer that X is likely to be small. And 0.1 plus a really small number is still just going to be 0.1. So if I have 0.1 plus 0.00001, that's for all practical purposes still just 0.1. And so just like we learned in the acid-base chapter, so when X is small, again, inferring based on having a small equilibrium constant, then when you add it or subtract it, you can pretty much ignore it. And the key is, as long as it ends up being less than 5% of 0.1, then it was not statistically significant, and it shouldn't have a huge impact on us solving for X here. And so if we rewrite this here, we're going to get 1.8 times 10 to the negative 10 is going to equal 0.1x. We'll divide both sides by 0.1. And dividing by 0.1 is the same thing as multiplying by 10, and so we can actually do the math pretty easily in our head here and get 1.8 times 10 to the negative 9 molar. And that is our new molar solubility. And so if you look here, this is significantly less soluble now than it used to be in pure water based on the presence of a common ion. So in pure water, we got a molar solubility of 1.3 times 10 to the negative 5 molar. This is now down to 1.8 times 10 to the negative 9 molar due to all the chloride that's present in our solution. So that represents like close to a 10,000-fold reduction in solubility. It is a significant difference here. And so our common ion effect, so again, it is reducing the solubility here because we had some strong electrolyte in the solution that's producing either silver or chloride and putting it into that solution effectively 100%, being a strong electrolyte. So that's kind of the deal here. So notice my shortcut I brought up before where I like, well, you know, just go, there's one silver, so 1x to the 1 power, and one chloride, 1x to the 1 power. Again, that only works for just plain old solubility in water with no common ion present. If you've got a common ion present, it's not simply going to be 1x to the 1 power times 1x to the 1 power. So in this case, notice that turned into 0.1 plus x. And we ignore the plus x, but notice that extra x just drops off in this case. Also note that the x was definitely statistically insignificant. That is way less than 5% of 0.1. So way less. And so ignoring it, good call. Had we used the quadratic, we would have effectively got almost exactly the same answer. Let's take a look at the next one here. So what is the molar solubility of Ag2S in 0.001 molar AgNO3? So the key here is that AgNO3 is a strong electrolyte. If you go back to your solubility rules, all nitrate salts are soluble, all of them. And so your strong electrolytes included either strong acids, strong bases, or soluble ionic compounds. So in the first example, we had HCl, which was a strong acid. Now we have a soluble ionic compound in AgNO3. And so we're looking at Ag2S. And for the Ksp, that's going to dissolve into 2 silver ions and a sulfide ion. And the Qsp expression Ag plus squared times the sulfide concentration. And one thing I highly recommend if you're doing a problem that you recognize as part of solubility equilibria, but you're not sure where to go, first thing I would do in any problem is probably write the solubility equilibrium reaction, solid dissociating its ions, and then write the Qsp expression. Great place to start for just about any problem you're likely to encounter. Now in this case, we're looking, what is the molar solubility? And when you hear that, you should be like, oh, they're asking me to solve for X. But in this case, they say in 0.001 molar AgNO3. And so AgNO3, being a strong electrolyte, will dissolve completely to give Ag plus and NO3 minus. And I couldn't care less about the NO3 minus, but the Ag plus I do care about. It's a 1-to-1 ratio here. And so in this case, 0.001 molar AgNO3 is going to give us 0.001 molar silver. Note that had there been a 2 in front of here, then maybe it would have been a 1-to-2 ratio. I would have had to double it, but not the case here. Still 1-to-1, so 0.001. And so we go to fill out this ice chart here, and instead of 0 and 0 like we had in pure water, so here we're going to have 0.001 molar. So, and we're going to have plus 2x and plus x. And 0.001 plus 2x is simply 0.001 plus 2x, and 0 plus x is x. And that's what we're ultimately going to substitute back in here. So the Qsp value is given once again as 6.0 times 10 to the negative 51. And the silver ion concentration squared, I think I'm going to need more room than that, 0.001 plus 2x all squared, and then times the sulfide concentration of just simply x. And this is even worse now. Now we've got a cubic equation. You're actually going to have some x cubed terms and stuff like this. And again, you're never going to have to solve those. So in this case, we're going to once again assume that x is small. And again, when you multiply or divide by a small number, it has a huge impact. It's only when you add or subtract it that it often has very negligible impact. And so we're going to assume not only that x is small, but even if you double it, it's still going to be way smaller than 0.001. And again, with an equilibrium constant of 10 to the negative 51, that is super tiny. We should expect a really, really small value for x here. And even doubling it, I'm going to expect that going to be way smaller than 0.001 here. So in this case, if we work this out, 6.0 times 10 to the negative 51 equals, and we're going to have 0.001 squared. Notice 0.001 is 1 times 10 to the negative 3, and if you square it, you're going to get 1 times 10 to the negative 6, and then times x. And if we divide through by that 1 times 10 to the negative 6, we could probably do this in our heads. We're going to get 6.0 times 10 to the negative 45 for our molar solubility now, which again is considerably smaller than the molar solubility we got in the last lesson for Ag2S when there was no common ion present. Okay, so this is the common ion effect you should conceptually understand. Then again, adding any strong electrolyte that either has silver or sulfide in this case is going to reduce the solubility of silver sulfide here. And then mathematically, you should understand how it changes our calculation. And again, the only change is that in our ice table, we have one of the initial concentrations is not going to be 0. It's going to be whatever the concentration resulting from the addition of that strong electrolyte is. So now we're going to deal with precipitation. So in precipitation, classically is just simply the formation of a solid in a solution. So solid in a solution, I like to think of it as a snow globe. When you shake up a snow globe, you see all these flakes floating around and stuff like that. And that's kind of what precipitation looks like. You might be mixing two clear liquids, but all of a sudden you're going to have like a milkiness form. And if you wait long enough, most of the time that milkiness will actually settle out and form a pellet on the bottom of your test tube or beaker or Erlenmeyer or whatever you're using. So, and that is precipitation. It's just got an aqueous solution oftentimes, and you're going to be forming a solid in that solution. Cool, let's talk about this a little more in the context of a problem. So, problem says, what is the maximum concentration of hydroxide present in a solution with Mg2 plus equaling 0.01 molar? And then it gives the Ksp of magnesium hydroxide is 1.6 times 10 to the negative 12. And this could be a little bit confusing for students. They're like, why did they give me the Ksp of magnesium hydroxide? What's going on here? Well, again, good place to start. If you recognize a problem is solubility equilibria related, write out the Qsp reaction and the Qsp expression. And since they gave us the Qsp for magnesium hydroxide, then we're going to write out the Qsp reaction for magnesium hydroxide. So magnesium hydroxide solid is going to dissociate to give 1 magnesium ion and 2 hydroxide ions. The Qsp expression is simply Mg2 plus, that's a really ugly 2, times the concentration of hydroxide squared. So we started this off good here. We're told that the magnesium ion concentration in the solution is 0.01 molar, and they're asking for the maximum concentration of hydroxide present. So what you really got going on here is relating to something we might call Qsp. So in Q, here's the reaction quotient, same one we encountered a couple chapters back. It looks a whole lot like the Ksp. So with one key difference. So the Qsp has the magnesium and hydroxide concentrations included at anywhere along the way. You might be at equilibrium, you might not. Whereas for Ksp, we don't write it in, but it's implied that these concentrations have to be measured at equilibrium for this product here to equal Ksp. And so what we're going to be doing is comparing Qsp to Ksp. So because here this salt is going to dissociate into a cation and an anion if you actually start with the salt. So however, what if you start in a solution that you don't actually get to start with the salt intact and see it dissolve, but you actually start adding some magnesium and hydroxide ions into the solution and see if they come together, cation with anion, opposite charges, to form some of the salt. Forming some of that solid would be a precipitation. And so precipitation is actually the exact reverse of these solubility reactions we've been writing. And so what you're in this case, you're not starting out with any solid at all. You're starting out with the products instead. And if you add enough of them, then they won't be able to resist each other. Notice cations are positive, anions are negative. They won't be able to resist each other, and they will bind together to form some solid. And it's different for different sets of ions based on the Ksp value. And so the way this works, we're going to be actually calculating a Qsp, so based on having some of these magnesium hydroxide ions in some cases. And the idea is this: the Ksp describes the maximum amounts you can have in your solution, either because you have a saturated solution of the solid, and so as much as could dissolve has, or you just have the highest concentrations that are possible. So in that solution before they hook up together and form some precipitate. If you go over that maximum possibility, so then the ions, that's when they do come together and this equilibrium shifts to the left, causing these concentrations to go back down until they're back to equaling Ksp. All right, now here's the deal. We don't have an ice table here. Notice when we set up an ice table, a big part of setting up the ice table for one of these Ksp reactions was to put a minus x here for the amount of solid that is dissolving. Well, again, in this question with precipitation, we're not starting out with any solid. We have a solution that has magnesium in it, and we want to know what's the max amount of hydroxide that could be in that solution. And so there's no evidence that we have any magnesium hydroxide to begin with at all to start with, which means we don't have any that could dissolve, and there's no point in setting up an ice table. So that's the first thing. There's no ice tables, which means there's also no x's as part of our calculation here. So typical calculations often are just going to be using either Ksp or Qsp and plugging in the numbers that you know. And so in this case, the question is, what's the maximum amount of hydroxide? Well, again, the Ksp describes the product of the maximum concentrations that could exist in that solution. And so that's the indication we're going to be using this Ksp here, and we're going to be solving for that hydroxide concentration. And so in this case, we're given the Ksp, and once again, it's 1.6 times 10 to the negative 12. We're given a magnesium concentration of 0.01 molar, and then we're just asked to solve for the hydroxide concentration and go from there. I didn't have to substitute any x's in or anything like this. Again, x is called the molar solubility in these ice charts, and that's when you're actually dealing with solubility, the reaction going in the forward direction. But when you're concerned with the reaction going in reverse, you haven't started out with any of the solid at all, but you might be forming some, then there's no point to an ice table, no point to x's. We're not substituting any x's in here whatsoever. So, and I emphasize this because the students often don't realize this, but notice we've now come up with 3 different ways of solving questions. We dealt with, setting up an ice table and x's in molar solubility questions. Then we did molar solubility with a common ion present, and it still involved an ice table, but one of your initial concentrations was not going to be 0. And now we're looking at a precipitation reaction dealing with maximum concentrations that could be in the solution, and there's no ice table to even set up in this case. We're worried and concerned about the reverse reaction happening, which might form solid. And so in this case, we're just going to solve for this. So if we divide through by 0.01, we're going to get, dividing by 0.01, same thing as multiplying by 100. So we're going to get 1.6 times 10 to the negative 10 equals the hydroxide ion concentration squared. And then we'll just take the square root of both sides to get that hydroxide concentration. And so if we take the square root of 1.6 times 10 to the negative 10, we're going to get 1.3 times 10 to the minus 5. Cool, and that is the answer to this first question. In principle, actually a little bit easier than anything we did with an ice table or anything like that. We just plug the numbers we had into the Qsp expression, solve for the one we didn't. There's 3 variables in here. The Qsp was given, the magnesium concentration given, and then we just were asked, what's the hydroxide concentration, the maximum that could exist in that solution. Cool, let's see how else we might see a precipitation question. All right, so next way these could be asked. Next question says, to a solution of 1.0 times 10 to the negative 4 molar magnesium nitrate, NaOH was added to a final concentration of 2.0 times 10 to the minus 4 molar. Did a precipitate form? And then once again, the Ksp of magnesium hydroxide is provided. And so a little bit different problem here. So we're asked if a precipitate forms. Now here's the deal. Again, if you recognize this is part of solubility equilibria, even though, again, this is not technically solubility, but it's going to be about precipitation, the reverse reaction, we still work it off the Qsp reaction. And again, we're provided with a Qsp. So again, write the reaction, write the Qsp expression. Good place to start here. And once again, quite common in these questions is to be dealing with Qsp as well. And again, the Qsp describes the maximum concentration of ions that could be present in the solution and it be at equilibrium. So the Qsp, we could have a couple different situations. Let's just say you're adding a little bit of magnesium hydroxide in there. Well, you could add so little that you haven't reached the maximums, in which case your Qsp would be less than your Qsp. And in that case, you just have an unsaturated solution. You're below the maximum concentrations that could exist in that solution. So, or you could add up right up to the threshold where Qsp equals Ksp, and in that case, you'd have a saturated solution. So here we had unsaturated, and here we're going to have saturated. Those are my abbreviations for saturated, unsaturated there. So, however, you could have one other situation where you've added such high concentrations that this multiplies out to be higher than the maximum normal allowed amount. And so Qsp would be greater than Ksp. Well, that can't stay that way for long. If we call, Ksp here the maximum amount that could be the solution and be at equilibrium, well, then something's going to have to happen if we're higher than that amount to lower those concentrations back down so that we're at equilibrium. And that's what's going to happen. This equilibrium, this reaction here is going to shift to the left. Just like we learned before, when Qsp is greater than Ksp, the reaction is going to shift to the left. We learned that back in the Le Chatelier's principle lesson. And so this equilibrium is going to shift back to the left to form some solid. And so a precipitate is going to form, and that's going to cause these concentrations to go down to going back to where they're just equal to the maximum allowed concentrations in that solution to be at equilibrium. And so when Qsp is greater than Ksp, that is the evidence that a precipitate is going to form. Cool, so quite often in a question like this, to a solution again that is 1 times 10 to the negative 4 molar in magnesium nitrate, 2 times 10 to the negative 4 molar in sodium hydroxide, and the question is, does a precipitate form? Well, first thing you got to figure out, well, what precipitate are they talking about? Well, usually they have to give you the Ksp for that precipitate. They gave it the Ksp for magnesium hydroxide. And so the key is this: we have magnesium nitrate, and again, all nitrate salts are soluble, so that's a soluble ionic compound, an example of a strong electrolyte. And so since it's going to dissociate completely, I'm going to get 1 times 10 to the negative 4 molar magnesium and then double the amount of nitrate. Well, I don't care about the nitrate. The nitrate's not part of the relevant equilibrium here. It's only that magnesium I'm worried about. And in this case, that magnesium concentration is also going to simply equal 1 times 10 to the negative 4 molar. And in the sodium hydroxide, that's a strong base, another strong electrolyte. It dissolves completely to give 1 sodium and 1 hydroxide. And so the sodium ion concentration is also going to be 2 times 10 to the negative 4 molar, and I don't care about it at all. It's not part of my reaction. It's the hydroxide I care about. And that hydroxide concentration is also going to be 2 times 10 to the negative 4 molar. And now that I know their concentrations in this solution, what I don't know is, are we at equilibrium? Are we at the maximum? I have no idea. And so I'm actually going to be calculating Q, not K, but then I'll be comparing it to the provided Ksp value to see which of these 3 scenarios we're in. And so in this case, the Qsp equals the magnesium concentration, 1 times 10 to the negative 4, times the hydroxide concentration squared, and the hydroxide concentration is 2 times 10 to the negative 4. And we probably do this in our head. So 2 times 10 to the negative 4 squared is 4 times 10 to the negative 8. And then times another 1 times 10 to the negative 4 is going to be 4 times 10 to the negative 12. Now, technically, if we add one more sig fig here, 4.0. Well, again, the Ksp provided is 1.6 times 10 to the negative 12, and 4 times 10 to the negative 12 is a little bit bigger than that. And so right now, our Q is bigger than the provided Ksp. And if Qsp is bigger than Ksp, then yes, a precipitate forms. Cool. So pretty run-of-the-mill question. Now, if a professor wants to get tricky, they're going to ask a very similar question with one important twist, and it's going to get very tricky in a hurry, but it'll involve only all principles that you've already learned. So it's not hard, but it is tricky. All right, so this next one says 50 milliliters of 1 times 10 to the negative 4 molar magnesium nitrate was mixed with 50 milliliters of 2 times 10 to the negative 4 molar sodium hydroxide. Did a precipitate form? And you might be like, that's exactly the same question, Chad, except that it isn't. So notice if I mix 50 milliliters of orange juice with 50 milliliters of water, what happens to the concentration of my orange juice? it goes down. It just got diluted. The same thing's going to happen here. So here we were saying that this is the concentration of the magnesium nitrate, but it's not the concentration in the end. It's the concentration before we mixed them. And so if we use 50 milliliters of this solution and 50 milliliters of this solution, we're going to find out that they're diluting each other. The concentration of magnesium nitrate is no longer going to be 1 times 10 to the minus 4, and the concentration of sodium hydroxide after mixing is no longer 2 times 10 to the negative 4 molar. They've both gone down. And you might recall for dilutions, we use M1V1 equals M2V2. So for dilution calculations, we want to find out what's the final molarity. Well, in this case, like for the magnesium nitrate, let's say, we have the initial molarity is 1 times 10 to the negative 4 molar. The initial volume is 50 milliliters. Final molarity is what we want. And the final volume after mixing is a total of 50 plus 50, 100 milliliters. And solving for M2, we'll divide through by 100, and 1 times 10 minus 4 times 50 over 100 is just half of, essentially 1 times 10 minus 4 times a half. And that's going to get us 5 times 10 to the negative 5, equal to our final molarity in the solution. So it turns out real common to mix equal volumes of 2 solutions. And one thing you should just kind of take home with you is that when you mix equal volumes of 2 solutions, the molarities are all cut in half. So just based on what we found right here. So if we go back here now and recalculate Qsp using our new molarities here. So in this case, the magnesium nitrate solution is not going to be 1 times 10 to the minus 4 anymore. After mixing, it's actually going to be half that, 5 times 10 to the minus 5 we saw. And same thing with the sodium hydroxide. After mixing, it's no longer going to be 2 times 10 to the minus 4 molar. It's going to be 1 times 10 to the negative 4 molar. And we'll go back and calculate Qsp one more time. And so our magnesium concentration in the solution after mixing is 5 times 10 to the negative 5 molar. And for the hydroxide, 1 times 10 to the negative 4 molar. And if we multiply these out, we're now going to get 1 times 10 to the negative 8 times 5 times 10 to the negative 5. And that's going to get us 5 times 10 to the negative 13 for Qsp. And again, Ksp is still 1.6 times 10 to the negative 12. And so our Qsp is now less than our Ksp. And we simply have an unsaturated solution. There's no precipitate going to form. This equilibrium is not going to shift to the left to form any solid whatsoever. So super tricky way to ask it there. I just want to make sure you saw one example of that as well before you started doing some practice on your own or before you encounter it on an exam. Now, if you found this lesson helpful, that thumbs up button is super helpful to the channel. If you're looking for practice on general chemistry, if you're looking for final exam rapid reviews or practice final exams, check out my general chemistry master course. I'll leave a link in the description. A free trial is available. Happy studying.